So we'll get to the recording, and within this recording, as everybody just keeps talking, but that's fine. It's not like I gotta listen to this again. We've got the mechanisms written out. So if we take a look at this first mechanism from our elimination lab, it's a little bit small down there, but I thought I understood. This was for our acid mechanism, so I appreciate the extra note. That was nice. And so if we go through and look at the acid mechanism, our alcohol goes through protonates first, turns into water as a great leaving group, leaves us the carbocation. We then have two beta positions, they labeled HA and HB, which can then go through to produce two different products. So we get HB or HA. As was also noted, there's a third, technically, beta hydrogen. That third beta hydrogen is the same thing as HA, so it's just producing another product from a different point of view. Right? When we look at this product or this mechanism, at least as we've discussed it within lecture, we would predict the more favored product would be the more stable one. So the double bond that was more substituted. Okay? Why? Okay? Yes, it's more thermodynamically stable, but isn't HA more accessible? Well, yeah, but in the speed of this reaction, do we care? If we're talking about the speed of this reaction, since it's an E1 mechanism, formation of that carbocation, our rate is going to be equal to the rate constant times the concentration of our substrate. And really, that's the substrate, trust me. We really don't care about that base step. So all we're focused on is no longer speed and now only thermodynamics, which means the only product that we should expect to get out of that would be our thermodynamic product. Right? You're shaking your head?
What?
Just checking. No? Okay.
I'm good.
So if we were to go through and look at the results of our experiment, okay, this is where the class should have taken notes because I deleted everything. Actually, I was going to record it and leave it in there, and then I started laughing, and I thought my laughter should not start the video off. What was the result from the acid addition? We've got our 2-bute, which is our thermodynamic product here. And then our 1-bute, what was our ratio?
It was 5.6 to 1.
5.6 to 1. So we're seeing a pretty substantial favoring for the 2-butene product. Okay, so that matches our mechanistic understanding behind this. That's kind of cool. We're getting experimental evidence that supports this. Okay, one of the things that's a bit misleading when we consider lecture versus lab, and in lecture we just say, what's our product? It's the thermodynamic and we're done. It's always more nuanced than that, and we can produce some of those other products. We just generally say that those other products weren't relevant to our overall discussion, and so we tend to only hyper-focus on the major product when we deal with organic chemistry lecture. Okay? Which is going to become a bit problematic when we move into the next one when we talk about the base mechanism. Assuming everybody's good with pictures, it is recorded.
I know, but I don't want to listen to the whole thing. I'm sorry, it was 3 hours.
Well, no, I'm breaking it up. This would only be 3 minutes to get to this point.
Oh, then never mind.
Okay. But I understand. Listening to me once is enough. Some people are like, it was more than enough. Okay, so for our base mechanism, we've got the other thing written up, and now when we're running with the base, using that strong base of our DBU, this changes our mechanism to run under E2 conditions, which means it all has to happen at the exact same instant. Okay, we still have the two possible beta hydrogens. And I don't remember if we think to the previous one, this was calling this one HA, and this one was HB, right? Nope, I drew it backwards from the previous thing. No, I did it right. HB, and this one was HA. If we're matching it to the mechanism that was already written up there in the 30 seconds ago within the recording. Okay, so if we're looking now at these two mechanisms, we still get those two potential products depending on what hydrogen we're removing. Again, because there's two beta hydrogens to choose from. So we drew out that mechanism, and now again we have to ask ourselves, is there a favoring for one versus the other? Well, under E2 dynamics, everything's happening at the exact same instant, which means the base has to come in and remove the hydrogen at the exact same time as the leaving group leaves. This crowds everything into one crucial step, which now means I have to take into consideration speed, the kinetics and the feasibility of getting that base into the place to do the chemical reaction. So now that we're factoring in speed, which is more accessible, HA or HB? HA. We're looking at HA as a primary versus HB being a secondary hydrogen to remove. We have an extra layer on top of it. HA is actually duplicated because the two methyl groups are identical. So according to lecture, what we'd be saying is that with that strong, bulky base, we'd be driving for this product, our kinetic product. And that would then be our major product. This one gets a bit weird because it's not the thermodynamic product. It runs counter to what we would expect as far as stability and energy, which is why when this product is made, it's named anti the normal way. The normal way is typically referred to as Zaitsev's rule. We're going anti-Zaitsev. Right? Or another person came in and actually ran some more experiments to really push it over the top and force the kinetic product over the thermodynamic in an E2 mechanism. And so that product, our kinetic product, can be named after that person, and that's Hofmann. So you'll sometimes hear reference to a Hofmann elimination, okay, or anti-Zaitsev. Both of those are referencing ultimately the same concept. Right? So what does that mean to us as far as our reaction? Well, if we go through and now look at the experimental real world, what did we go through and know? This was our 1-butene, our 1-but versus our 2-but. And when we go back and look at that ratio, this class is going to tell me what those numbers were in a second here. We had 1 of the 1-but and we had 3.34 for the 2-but. So according to experimental evidence, the 2-but was still the primary product. Okay, could we come up with an explanation for why? Why? So how long we took, didn't the reaction happen almost instantaneously? And if it's going to happen really fast, shouldn't that favor the kinetic? And here we're favoring a thermodynamic. Okay, where I would push is that we're probably looking at the amount of heat that we've put into the system, and that heat was enough to kind of trigger a little bit of thermodynamics. Perhaps also that the 1-butene was so reactive that it reversed very quickly under those conditions and allowed for the formation of a thermodynamic to a certain extent. Okay? So this chemical result tends to run a little bit in the face of what we're being taught in the lecture, but that's kind of how the world works, unfortunately. So the lecture is trying to set you up with kind of the broad ideas of what theoretically should happen, okay? And the real world doesn't necessarily perfectly align. So why is the lecture pushing this? Well, I would argue the lecture pushes that differential because what we're trying to do is emphasize not that thermodynamic is more stable than our kinetic, but that when we look at the E2 versus the E1, do we see a difference in the end result? When we ran the E2, we've got the ratio that we're seeing, but when we run under E1 conditions, we're seeing, I already forgot, was it 6? It was 5.
5.6.
5.6 to 1. We're seeing a significantly larger favoring when we look at the E1 mechanism. So what the lecture is really doing is polarizing that as much as possible. Why? To help you navigate the lecture faster, more efficiently than having to get into the nuances of what we're talking about within the lab. Kind of makes sense? So the lecture is really just saying, look, these are so different. Lab shows a little bit more nuance behind those individual systems. What I want you to really pull is lecture isn't perfect, but it does set up some of those larger patterns that we're seeing. We are seeing E1 favor much more heavily the thermodynamic than we are for the E2. And so the E2 does get a increased favoring for the kinetic, and depending on our circumstances, may or may not. result in the pure kinetic product. Kind of, sort of? Okay. At that point, I believe we've now done everything as far as the elimination post-lab. Right? You now have to put this all into your own words, organize it, and put all the structure together. Do you need the mechanisms? I don't think so, right? To do the explanation. The explanations that you guys provided was what you needed. We use the mechanisms to help kind of force that conversation to allow you to get to those conclusions. Does that make sense? I believe the first question in the post-lab asks for a mechanism, okay? But that's not strictly necessary within this, right? To answer these parts of the questions. I'll also add, I believe the post-lab says there's 3 possible products. That's an typo copy-paste issue from when we did a different experiment. So I went through, and for a different experiment that was doing an elimination, we still needed a mechanism. I was like, oh, we still need a mechanism. I'll just change the name of the compound and we'll be done. I should have read through it a little bit more detailed because in the previous experiment, there were 3 distinct possibilities. In here, there's really only 2 distinct possibilities. Right? Some people have asked about that. Make sense? Okay. This video is going to get a little bit weird because we're still going to talk about data analysis, but now we're going to shift away from the addition and into the ionone. Okay. So the ionone for our addition. So sorry for the scrolling. Oh, I remember how this works. Sorry for the scrolling again. The ionone is set up a little bit differently. If you guys remember from the actual lab, there was no background information. I didn't give you any background information because I didn't write any. That was pretty much the lesson. What I could have done was give you this background information that is in the group data document. The reason why I didn't give you that background information is it had a lot of answers within it that I wanted you to think about after doing the experiment, not see before the experiment. Right? So if we go through and look at this, okay, we're going to look at it in more detail. Well, actually, we're not going to look at it in that much more detail. But if we go through and jump to kind of the end, if we remember the ionone experiment, we said that there were 3 possible products. Okay? If you also remember the conversation that we had, I screwed up the mechanism. I screwed up the mechanism last week because I forgot a methyl group. As soon as you add the methyl group, the mechanism comes into play and all 3 products become visible and accessible within it. We will look at that mechanism in a little bit. That's, I would argue, starts to shift more into the introduction or writing the lab report part. Okay? Data analysis, what we've got in this document are now 2 NMR spectra that are going to be of particular relevance. So we'll zoom in. Come on, stop being a punk. Okay, for figure 2, and figure 2 shows us the NMR for the beta ionone. Okay, so one of the ionone products. And if you go through and look at this, how many unique hydrogens are there? Well, the structure is really small. All those little colored balls represent unique hydrogens. Okay, do you all think you're good enough at NMR spectroscopy to be able to assign all of those? No. Cool. No offense. I didn't think you were either. I also don't think I am. Okay, to add reverse salt, I guess. Okay, so if we're considering that system, how would we be able to go through and interpret? So if we went back to your spectra, your NMR, how could you look at that NMR and possibly know which of the ionones you have? Okay? I don't expect you to. What I expect you to be able to do is to look at this NMR and now go to this document and be like, does it look like this one? Yes? Which product do you have? You have the beta ionone. So what we're doing is a matching game. That's all we're doing as far as the NMR. A little bit more than that, and we'll look at that in just a second. But that's our primary focus. Does that make sense? Okay. What's the little bit more than that? So again, back and forth. Let's take a look at, yeah, this one looks okay. Let's do this one. Where'd it go? Does this one look like the beta ionone? So there's the beta ionone. There's this one. So theoretically what you're doing is looking in this range, because all of that is confusing as hell to interpret, and all you're looking at is the kind of unique system. So if we scan through that system, we've got a whole bunch of different peaks in there. It still does look kind of nice as a spectrum. Whoops. But we look here, there's really only 4 peaks, right? And if I go through and look at this document, I got a whole lot more than 4 peaks. Why do I have more than 4 peaks? There's more unique hydrogens in there, or more different hydrogens. Why are there more different hydrogens? I don't have just beta ionone. Maybe I have alpha ionone, or the gamma ionone. Okay? Or maybe I have a mixture of them. Okay? So what we're trying to do is to look at that range and come to a loose interpretation, a qualitative interpretation that will address the qualitative aspect in a little bit. But for these conditions, okay, if we scroll back up, room temperature with phosphoric acid isn't producing pure beta ionone. It's producing a mixture. Okay? That's what we're seeing out of that. Okay? Is it a mixture with alpha ionone? Well, what does alpha ionone look like? This is where we could go back to the spectra and go over and look at figure 1. Take a look at figure 1, and you're like, oh my God, what a giant friggin' mess. There's even more peaks in it. And if we read real carefully through the footnote here, see all these little red things floating around? Those little red things happen to correspond to the beta ionone. All the little colored circles correspond to alpha ionone. Okay? And if we look, they're really similar to each other. They're slightly different, which makes sense because of the placement of the double bonds. We'll talk about the structure when we look at the mechanism behind those. Okay? But that's what we're trying to navigate through. Does that kind of make sense? What conditions were this one? This was the mixture with phosphoric acid. Oh, interesting. If we go back to our group data, this thing was produced under what conditions? We scroll back up. Fascinatingly enough, phosphoric acid. Okay. I think that's really freaking amazing, and nobody else seems to care. Okay. If you consider what a group of your colleagues went through, did this experiment, and obtained an NMR that looks almost exactly like the NMR of a high-level chemist, are you not entertained? Like, come on, that's freaking awesome. You guys are able to replicate the results of somebody that's been doing this for 20 years. That's fantastic. You're totally
I'm sorry,
not
I'm
entertained.
like not.
I'll take my
I'm like
Okay? I think that's pretty cool. If you go through and look at the phosphoric acid, or sorry, this one that was the nice clean beta, that was sulfuric acid and glacial acetic acid. Why should we go about that one? We didn't use glacial acetic acid for any of our experiments. Okay, so we can't get a perfect comparison to that, but if we go back and look at our spectra for a group that actually submitted it, that one's not bad. This spectra looks an whole hell of a lot like this spectra. What does that mean? Sulfuric acid in water at room temp has almost identical results as sulfuric acid and glacial acetic acid. Why does that become an important observation? Okay. This now pushes into kind of goals behind this experiment. We ran 4 different tests. Okay. We ran 4 different tests because we were trying to make one of these ionone compounds and in a yield. Why? Because that compound was valuable and useful. And if we can make that compound cheaper, more efficiently, we can corner the market and sell more of that compound, all that kind of fun jazz. Glacial acetic acid. Let's not worry about the glacial. Acetic acid versus water. Which one's safer? Water. And because it's safer, guess what else it is? Cheaper. Which means if we look at our synthesis versus this glacial acetic acid one, ours is a better synthesis. Okay? Because we're producing roughly the same purity according to NMR, okay, using safer chemicals. That's awesome. Okay? You should read through this document, okay, this background information. This provides a lot of the kind of context behind what the experiment is for. It's not technically written for students. It's written for me to be able to look at it and be like, I can make students do this experiment so that you can analyze these things. Okay? Instead, I took it to be like, well, let's just do it all together. Okay? Let's take it as a learning lesson all the way through. And when we continue through this, you'll note that they get this fun little table, okay? The impact of the reagent on what product you get. And so if we look at phosphoric acid, 85% at room temperature, what was the ratio? We got a 77% alpha ionone, okay, to 23% beta ionone. How can they figure out that ratio? We could leverage our NMR and look at the area underneath the curve for those individual signals, and we could come up with that ratio. Okay? But that kind of requires something kind of important. What's that something kind of important? Where is it? Where'd it go? Am I looking at the right one? I am. One spectra looked better than the other, and now I'm confused. Let's just look at this one. What would I have to go through and do? How many peaks are there? A whole bunch. So what do you have to do? You would have to differentiate which one belonged to which hydrogen so that you could make your area underneath the curve. To get the area underneath the curve, what did we do with the previous experiment? We zoomed way the hell in so that we could make the measurement, right? Not only did we zoom really far in, we also blew it up onto our projector so we could bust out a ruler to measure this. Those peaks are going to be really hard to go through and do that on, particularly considering I didn't provide a zoom in. Why? Because I'm an idiot and I freaking forgot. Okay? Give me a break. Okay? But this is where what we'll do is the qualitative interpretation. You can qualitatively ballpark, it's definitely a mixture. Okay, I'm going to compare this peak to this peak because I think those are the ones that belong to alpha and beta. And because these are sharper peaks, we could probably get away with just the height of the peak. And so you could ballpark estimate your favoring. Does that make sense? Okay. I think this would be a perfect example to use the NMR for. Okay. So when I saw these ratios, I got excited because I was like, oh, this is the first case. Because we did this lab before we did the elimination in the past. This would be the first case where we could actually leverage NMR in a quantitative fashion. I thought that was awesome. And then I read the stupid little footnote for this B for the alpha-beta ionone ratio. Calculated from using refractive index. As in we had to bring in another technique to figure out this ratio. Fuck that. Okay? So what you're going to do is ballpark estimate those. Okay, they don't have to be perfect. I'm not expecting everybody's data to come out the same. I'd be expecting them to come out ballpark reasonable. Okay, so if you say it's 70-30 and someone else says it's probably even 90-10, I'm okay with that. But if you say it's 70-30 and somebody else says it's 10-90, now I'm probably going to look a little cross-eyed at it. Does that make sense? You have 4 different experiments. Here they have 8 different experiments. Your times are all consistent. So including a table of time, or including the table with time in it, probably isn't relevant. Temperature, that is relevant. We actually modified temperature. Are these temperatures changed? Not really. Overall yield, can you determine an overall yield? Yep, so you'd be able to compare back to literature what they got. And then you've got a ballpark alpha beta ion ratio. What does that do for us? Again, what's your goal? You have to think back once you have all of this data and decide what that goal is. Is it just, I just want to study this for the hell of it? I want to make beta ionone? I want to make gamma ionone? I want to make alpha ionone? You have to decide what that goal is for your report. So within this individual experiment, I would argue you've got at least 10 different possible goals you could choose from. Okay? Once you've decided what it is, you will write your report centered around that goal. And we'll talk about that in just a second when we move into actually dealing with writing the report. Kind of, sort of? Okay. Some other data analysis things that we might go through and do that I think is kind of fun, that we did with the, or I did with the other class, Tuesday class. Okay, is we're just going to do some interesting scrolling. And in this scrolling, what I would like you to do is keep your focus on the IR. Okay, again, officially I think we've got 14 groups. This isn't bad. Maybe I've miscounted. Maybe we only have 12 groups. But if we do indeed have 14 groups, I would expect 14 groups for the data. Okay, we just scrolled through the IR. What did you notice? Different intensity of peaks around 3,000. That's fair.
When the peaks at 3,000 were really long, the stuff on the right became a little shorter. Or not as intense.
Or really long. Okay. So what I think you're seeing is just a relative intensity shift. So when that CH3 just gets really intense, that's going to make everything look shorter. I would actually bet that's probably due to some impurity getting in there and upping the amount of CH3s over the rest of the sample.
That's like an OH, right?
It does look like an OH. Small OH for those people looking cross-eyed at it. Okay, it's not a big OH, but there is enough there to suggest that there's probably some alcohol present.
It's more in group 3.
Do you want to hear what I saw? 3 different IRs. There were 12 spectra, though. Yeah, there were 12 spectra, but I could organize those 12 spectra into 3 different groups. Okay. Why does that sound kind of neat?
The alpha, beta, and gamma.
So that's possible. I didn't even consider that. That's neat. Cool, awesome observation. Alpha, beta, gamma, possible products. How many different experiments were there?
4.
There were 4 different experiments. So that we're seeing 3 distinctly different things. The first thing I want to go through and do is group all of the conditions and say, do all the spectra look the same within it? Okay? Because if all the spectra are looking the same, that's an awesome connection to make, that now I'm getting different results for those different conditions. And really I only saw 3 with 4 different conditions. So maybe 2 of those conditions produced the same results. Okay, what were those 2 conditions?
Temperature.
Well, that produced the same results.
Is that batch?
Okay. So what we'd now be navigating into is data analysis. How do you organize this massive amount of data to be able to come up with interpretations and groups and subcategories? Once you've grouped those things, because if we saw 12 different spectra, that's going to suck. Because that means there's 0 repetitiveness, repeatability within our experiments. We have repeatability. Different people are producing the same results, hopefully using the same conditions. That would suggest that we can now actually start drawing conclusions from that data set. That's awesome. This is another one of those you should be entertained. Like, that's pretty cool. Yeah, I totally feel much better when everybody cheers when I tell you to cheer. Okay? But that's pretty cool. We're actually getting results that you could now actually manipulate and potentially draw conclusions from and potentially publish. Like, that's really neat. You've done active research. Right? Which is part of when you read the background, they're like, we don't actually know how this works. We don't. We don't know why we would favor one versus the other. We just know that when we change some of those conditions, we get different products. So part of this would be, I'm getting these different conditions that cause different products. Now I'd want to know why. I have a repeatability to show that those conditions are favoring something. How are they different from the other thing? What other experiments could I add to change to see how that would either repeat and mimic or not? That's pretty cool. You guys, so. Go take a break.